Welcome to the 8th course of the optimizationcity.com, where we will explore the concept of the minimum cost flow problem. The minimum cost flow problem is a puzzle in the network optimization that asks for the cheapest way to route the given amount of flow through the network, considering the capacity limit and aiming to minimize the total cost. In this course, we have a four section to discuss. We start by introducing the concept of the minimum cost flow problem. Then we present the algorithm for this problem. Finding the initial solution, sometimes too tough. We follow it in section 3. And finally, we solve some example to clarify this algorithm. In the minimum cost flow problem, we want to distribute the same type of product from the factory to the sale market efficiently. We know the quantity of product produced at each factory and the quantity at each destination. Instead of sending the product directly to the destination, we can send them to the distribution center through the intermediate point if needed. So here point 2 and point 3 as the intermediate point. However, there are limits on how much can be transported on each transportation line. The objective is to minimize the cost of the transportation while meeting the demand and supply. Let's look at the simple example of the minimum cost flow problem using a diagram here. The nodes are shown as a numbered circle that are represented by node, and the arc are represented by arrow. The arc have a specific direction, meaning the arc or good can be transported through the one node to another at that direction. For instance, we can send the material from node 1 to node 2, but we cannot send the material from node 2 to node 1. We use the notation ij to indicate the arc going from node I to node j. In the diagram here, each arrow represents the path with a specific capacity and the cost for transportation. The capacity indicates the maximum amount that can be transported along that path, while the cost per unit represent the expense associated with each unit of transportation. For instance, in the arrow 2, 4, the flow can range from 0 to 4 as a capacity, and each unit passing through this path costs $2. The symbol infinity here indicates that there is no limit on the capacity at that particular arc. Moreover, the number in the parentheses next to the circle represents the available supply and required demand at each node. In this diagram, node 1 is a starting point with a supply of 20. Node 4 and node 5 are the destinations that require 5 and 15 units respectively, indicated by the negative sign. In the minimum cost flow problem, our objective is to discover the flow pattern that incur the lowest cost. To formulate this problem as a linear programming model, let's consider the following notation as a decision variable. Xij represent the quantity of unit transport from node I to j using arc ij. Now let it represent the linear programming model for the minimum cost flow problem in this figure. Equation 1 to 5 represent the flow balance equation in the network. Let's consider the balance equation at node 1 as an example. This equation states that, equation number 1, states that the combined flow leaving node 1, which is arc 1, 2, and 1, 3, and the flow is equal to x12 plus x13 should be equal to supply node at node 1, which is equal to 20. This ensures that the outgoing flow arc 1, 2, and arc 1, 3 match the available supply, which is equal to 20. So this is the equation number 1. Similarly, the balanced equation at node number 2 indicate that the incoming flow, which is arc 1, 2, is equal to outgoing flow from node 1, arc 2, 3, 2, 5, and 2, 4. The flow is equal to x24, x25 plus x24. This ensures that here, this ensures that the flow entering and leaving node 2 is properly balanced. We don't have any supply and demand at node number 2 here. The minimum cost flow problem has a unique structure that helps determine the solution algorithm. The flow variable denoted by xij in the balance equation have the coefficient of 0, plus 1, and minus 1, 0, minus 1, and plus 1, and so forth. Additionally, this variable appears precisely in two balance equations. Once with the coefficient of the plus 1 representing the node where the flow originates, and once with the coefficient of minus 1 representing the node where flow enters. Based on the above characteristics, the general form of a minimum cost flow problem can be expressed as follows. The model shown here represents the general form of the minimum cost flow problem. So how we can solve this model? In this part, we will learn about the Simplex network method, which built upon the network concept discussed earlier. The minimum cost flow problem is more complex than the transportation problem because it involves the intermediate node and the capacity restriction on the connection. To solve this problem using the Simplex method, we need to find the initial basic solution. This process is slightly different from the transportation problem and requires a significant effort. Let's assume that we already have an initial basic solution for now, but we will discuss how we can find the initial basic solution in the next section. We will illustrate the application of the Simplex network method to the minimum cost flow problem through an example here. In this diagram, each arc is labeled with two variables, A and B. A, the first component, represents the capacity of arc, indicated how much can pass through it, while B represents the cost of moving one unit through the arc. Now let's look at the initial solution that we will consider here. In this picture, the arc represented by dot line, dot dash dot dash dots, are a non-basic variable that reach the maximum capacity, while the solid arc represented by line are a basic arc. So we have 4 basic arc in this figure. This solid arc form a spanning tree which serve as an initial basic solution. To determine if this solution is optimal, we need to calculate the cost of all non-basic variable arc. To do this, we calculate yi value for each arc, where I range from 1 to n. If the calculated yi value satisfies a certain condition in the next slide, we can evaluate the optimality of the solution. This is the optimality condition for the certain basic solution. We will discuss these 3 conditions in the example. So how we can find the yi? To calculate the yi value, we can set one of the yi value to 0 arbitrary and determine the remaining yi value using the formula here. So Cij minus yi plus yj is equal to 0. Let's compute the yi based on this equation. If we set y2 is equal to 0, using the Cij minus yi plus yj, like here, is equal to 0, where 0 is the Cij bar for the basic arc, y4, y1, y3, and y5 can be calculated. Then the Cij bar for the non-basic variable are found. So the question is how to improve the current basic solution. To improve the current basic solution using the provided Cij bar for the non-basic variable, there are two options. First, increase the flow through an arc that has a positive Cij and is currently at the minimum limit. Second one, decrease the flow through an arc that has a positive Cij and is currently in the maximum limit. Considering this case, the only possible candidate is arc 4, 5. In the following diagram, we add arc 4, 5 to the network to determine which arc should be removed from the current basic solution. The effect on the flow of adding arc 4, 5 with the flow of theta to the initial feasible basic solution, that is the basic feasible spanning tree, is shown here. By adding the flow theta to node 5, there are two options to hold the balance equation again at node 5. First, decrease the flow of the internal arc that is basic into the arc to the node 5, or increase the flow of outgoing arc that is basic and from node 5. Here the first one is applied. Note that the arc 3, 5 is not a basic, so it's not considered into the option. So the only option that we have is arc 2, 5. Now the flow arc 2, 5 decreased by theta. The current value of the flow of arc 2, 5 is 10, so decreased by theta, the new value of the flow of arc 2, 5 is equal to 10 minus theta. So there are two, so there are two basic arc to consider to hold the balance equation at node 2. The arc 1, 2 is not a good option, because if the flow of arc 1, 2 change, for example plus theta, there is no any basic arc to enter or exit node 1 to hold the balanced equation at node 1. So we pick arc 2, 4 and update the flow. The flow balance equation on node 4 is hold, so it's done. Now the question is how much we can increase the theta. The capacity of arc 4, 5 is infinity, so theta can increase to infinity. The flow of arc 2, 4, that is 10 minus theta, should be positive, so theta can increase by 10. And finally, the capacity of arc 2, 4 is 4, so the maximum value of theta is equal to 2. As a result, we can increase the value of theta up to 2, which caused the arc 2, 4 to reach its maximum capacity and be removed from the basic solution. Consequently, the new basic solution is as follows. So this is the new basic solution. Based on this basic solution, we can set y2 again is equal to 0, and we can calculate the value of the yi for the basic variable using the equation here. So we can calculate y1, y2, y3, y4, y5. We set y2 is equal to 0, and we calculate y1, y3, y4, and y4 by using this equation. The cost Cij bar for identifying the input arc to the basic solution and the output arc from the basic solution are followed. So here at this point we can include arc to 3 into the basic solution because do not satisfy the optimality condition for the network optimization. To determine the output arc, we proceed as follows. So here we can increase the value of the theta up to 8 here, resulting in the removal of the arc to 4 to 5 from the basic solution. As a result, the updated basic solution is as follows. Using this basic solution, we can again calculate the yi by setting y2 is equal to 0, y1, y3, y4, and y5 is calculated based on this equation here. Based on a new yi, we determine the amount of Cij bar for the non-basic arc. For the non-basic arc, when Cij bar value are positive, the arc flow is at the maximum limit. When the Cij bar value are positive, the arc flow is the minimum limit. Therefore, the current basic solution here satisfy the optimality condition, and the current basic solution is the basic solution. Let's solve the minimum cost flow problem in the network Shine using the Simplex method in this network. So the first component is the capacity and the second component is the cost. This is the 20 supply and 20 demand for node 6. We utilize the provided initial solution here for the first step. In this step, the objective function for this network is equal to 380. Assuming y2 is equal to 0, we can calculate yi using the equation Cij minus yi plus yj is equal to 0 for all basic solution, basic arc. As a result, we can calculate y1, y2 is equal to 0, y3 is equal to 7, y4 is equal to 6, y5 is equal to minus 2, and y6 is equal to 3. The Cij bar for all non-basic variables are as follows. Out of the 4 arcs that can enter the basic solution, we select the arc 2, 4 because it has the largest absolute value compared to other. The output arc is determined as follows. As we discussed in the earlier example, as the arc 2, 5, okay, has reached the maximum capacity, it's removed from the basic solution. Therefore, the updated basic solution with the arc 2, 4 is enter the basic. We have the next basic solution here with the objective function of 295. In this solution, the objective function, as we state, 295. Assuming y2 is equal to 0, we can calculate yi using the equation Cij minus yi plus yj is equal to 0 for all basic variables. As a result, we have the yi for all nodes here. In the next slide, we calculate the Cij bar for all non-basic arc as follows. The arc 3, 5 can include into the basic solution because it does not satisfy the optimal solution. As a result, by setting the theta is equal to 5, the arc 4, 5, okay, is removed from the base, and arc 3, 5 include the basic solution. As a result of this change, the current basic solution is as follows here. And in this solution, the objective function is equal to 255. Assuming y2 is equal to 0, we can calculate yi value using the equation Cij minus yi plus yj is equal to 0 for all basic variables. As a result, We have the yi for all nodes, and we can calculate Cij bar for our non-basic arc as follow. As you can see here, the arc 1, 3 does not satisfy the optimality condition, then arc 1, 3 can enter the basic solution. So by setting a theta is equal to 10, arc 3, 2 is removed from the base and arc 1, 3 is added to the base. Therefore, the current solution is as follow. And in this solution, objective function is equal to 155. Assuming y2 is equal to 0, we can calculate again yi for all node as follows. We calculate Cij bar for all non-basic variable, then arc 6, 5, 6 is added to the base because it does not satisfy the optimality condition. So the arc 5, 6 enter the base, and as a result, by setting the theta is equal to 0, the arc 1, 2 is removed from the base and arc 5, 6 is added to the base. As a result, we have this objective function, this network with the objective function of 155. Assuming again y2 is equal to 0, we can calculate the yi for all node and Cij for all non-basic arc as follow. As you can see here, the optimality condition is met because Cij bar for all non-basic variable meet the optimality condition, that it's indicating that we have reached the optimal solution with this network. It should be noted that because theta is set to 0 in the current step, it caused a degenerate state where no improvement in the objective function value has occurred. And this is the optimal solution with the objective function 155. To create an initial feasible basic solution, we can use the method when it's challenging to such a solution, especially for a large network. This method includes introducing an additional node called V sub n plus 1. For node with the supply, we connect them to the Vn plus 1 by adding an arc with the cost of 1. On the other hand, for nodes with a demand or intermediate node, we connect Vn plus 1 to those nodes with the arc having the cost of 1. The remaining arc have a cost of 0. Next, we apply the simplex method to this network until the value of the objective function becomes 0. Once we reach this point with the objective function of 0, we have obtained an initial basic solution. We can proceed with the simplex method using this solution as a starting point. To find an initial basic solution for the given network, we can follow this step. So we create an artificial node called node 7. Connect node 1 to node 7 with the cost of 1 and the no capacity over arc 1, 7. And create arc from node 7 to all other nodes with the cost of 1. So 7, 2, 7, 3, 7, 4, 7, 5, and 7, 6. The cost of the other arc is equal to 0. The resulting basic solution is as follows. This is the initial basic solution for the simplex method for finding initial feasible solution. There are, as you see, there are arc from 1 to 7 and 5 arc from 7 to 2, 3, 5, 5, 4, and 6 with the cost of 1 and no capacity. So assuming y7 is equal to 0, we can calculate the yi coefficient based on the equation here. Cij minus yi plus yij is equal to 0 for all basic variable, our basic arc. So as we can see, we can calculate y1 to y6 and y7 is equal to 0. The cost of the Cij bar for all non-basic arcs is as follows. Because arc 1, 2 is at the lower bound and does not satisfy the optimal condition, it enters the base. So output arc can find using this process, as we stated in the earlier example, the arc 7, 2. Okay, the arc 7, 2 is removed from the base and resulting as a result, and arc 1, 2 enter the base. And this is the current basic solution. In this iteration, the value of the objective function is equal to 4t. Assuming again y7 is equal to 0, we can calculate the value of the yi for all nodes using the equation Cij minus yi plus yj is equal to 0. So we can calculate the Cij bar again for all non-basic arc as follows. Because arc 1, 3 is at the lower bound and does not satisfy the optimality condition, it enters the base. The output arc from the base can determine from this process. Arc 7, 3 is removed from the base and arc 1, 3 enter the base. As a result, this is the next basic solution with the objective function of 14 again. Assuming y7 is equal to 0, we can calculate the value of the yi for all nodes here from y1 to y6, and y7 is equal to 0. The cost of Cij for all non-basic arc is as follows. And you can see that the arc 2, 4 is at the lower bound and does not satisfy the optimality condition. So it enters the base, and the output arc can find using this process. So arc 7, 4 is removed from the base, and as a result, and arc 2, 4 enter the base, and as a result, this is the next basic solution with the objective function of 14. Assuming again the y7 is equal to 0, we can calculate yi coefficient using this equation, and this is the yi value for all nodes. Then we can calculate the Cij bar for all non-basic arc, and you can see that arc 4, 6 is at the lower bound and does not meet the optimality condition. So it becomes a part of the base. Let's determine the output arc. You can see that the output arc is with the theta of 10, the arc 4, 6 enter the base, but quickly reach at the upper bound because the capacity of this arc is 10 and remove again from the base. As a result, this change, the current solution is updated as follow here, but we have the same basic solution with the last iteration. So you can see that the list of the basic arc for this iteration is equal to this arc. As a result, we again calculate the Cij bar for all non-basic variable. As you can see that arc 4, 6 has reached its maximum limit and fulfilled the optimal condition. So we cannot consider this arc again for entering the base, but we can enter arc 3, 5 because it's at the minimum limit and does not meet the optimality condition. So it enter the base and find how we can find the output arc. by doing this process, and we can see that we add arc 3 5 to the base, and arc 7 5 is not longer part of the base, which lead to current basic solution as a follow with the objective function of 20. Again, we calculate the yi for all nodes, and we then calculate Cij for all non-basic arc as a follow. Because arc 5 6 is at the lower bound and does not meet the optimally condition, again it enters the base, and let's determine the output arc using this process. So you can see that here, okay, the arc 1 7 arc 1 7 removed from the base, here arc 1 7 removed from the base, and this is the basic solution for this iteration, and the objective function in this iteration is equal to 0. Assuming y7 is equal to 0 for, and calculate yi for all nodes, we can now calculate Cij. Now let's consider the cost of the non-basic arc, which as follow. The optimal conditions are met because the all Cij for all node for all non-basic arc meet the optimality condition. So we reach the optimal solution with the objective function of 0. So it means that this is the this is the final or optimal solution for this network, and we can use here the this solution for the initial solution for finding the minimum cost flow problem for this network here. Let's see. Okay, here. So we can use that initial solution for finding the optimal solution for this network. So this is the process we can use the initial basic solution for the challenge network. Okay, thank you so much. If you want more practice to improve what you have there, I've got something perfect for you. Check out my website www.optimizationcity.com, where you can find plenty of exercise to explore the minimum cost flow problem and improve your talent in solving this method. Thank you so much again for watching us. If you have any question, you can send an email by this optimizationcity@gmail.com, or you can visit our website www.optimizationcity.com and fill out the form. We will contact you as soon as possible. Thank you so much, and goodbye for now.